it's always interesting to go to events like this. So I usually try to start out a little bit about who I am, and people have been asking a few times why I'm here. I could be here for a number of reasons that include trying to describe how airplane purchase financing works, and a number of other things. But as Dale said, I've been involved in the computer graphics field. So I'm a computer graphics person. That's my background. I believe in visualization very strongly. I'm going to talk to you a lot about visualization and where Boeing uses it effectively and how we've influenced the industry. I'm a stand-in on Starship bridges. Have you noticed the great likeness that I have to Patrick Stewart? I know, that's exactly right. I know I have a career after, should I ever decide to retire from Boeing. As Dale pointed out, I've been around Boeing for a long time. We get along very well in terms of doing things, in pushing technology forward at a company like Boeing. And I have a tendency to have some reputation that I've built up over the years, and this has actually turned out to become international. I'm definitely a curmudgeon when it comes to something like virtual reality, where you try to immerse yourself in caves and other things. I want to find out a little bit about the demographic of the audience as I go through this. I'm an advocate for a field called augmented reality. Have any of you heard about this? We'll talk about it a little bit during the presentation today. What's most important from the talk that I'll present is to understand that the world that we know that we live in, and this is true for all of you who are in the sales business, who are in the manufacturing business, in terms of all this stuff, that we are awash in both geometric data and non-geometric data. What I'm going to talk about is a lot of the visualization techniques that we're trying to investigate and improve at Boeing, and have you understand and see how you can apply that to the world that you're involved with in terms of selling, building, understanding, financing, all sorts of things that deal with the housing industry. So this is basically why I'm here. Boeing builds stuff. I'm not talking to you as from a research lab or a university. I'm talking to you as a person who represents a company that builds what I think is really cool stuff. Okay, I have great thanks to Mark Ducharme for taking me around the aviation museum to hear. How many of you actually have gone through the aviation museum so far? If you haven't, go through it. It's fascinating to see how the Canadian aerospace industry has evolved over the years, and in many ways it mimics what's happened at a place like Boeing. We build all sorts of really interesting things, and there are technologies that are involved in building those aerospace products. It turns out that many of those technologies have some similarity to what's going on in the building industry. You have to understand the physics. Why are the three big bad wolves going to blow your house down? Right? You have to understand the physics of how all those things work. You have to understand networking, because it turns out that an airplane or a defense product is nothing more than a flying computer. As the evolution of housing goes forward, housing and buildings have tons and tons of sensors that require some care and feeding to make sure about the longevity of that home, of that property. There are real-time computing systems that we involve. So I'm a computer guy. How many of you are cursed with computers in this room? Is anybody who's not cursed with computers in this room? Okay, I've been doing it for a long time, and I've had a great time doing it. But we have continued evolution in the computing technology field. Boeing pays a lot of attention to material science. We build things out of exotic metals. We build things out of composites. There are interesting fabrication and process issues when it comes to actually constructing something like an aerospace vehicle. We do things in natural language analysis, because people try to communicate to us what difficulties are in terms of where there are problems in our products because, admittedly, there are occasionally problems. Some of you may have heard about the 787 fire, right? The battery that caught on fire. There are lots of things that we get through natural language, and we have to understand how to understand. We want to understand that better to gain more insight into what our customers are thinking, what the public is thinking, etc. When it comes to the bottom line, Boeing has one of just about everything that you can imagine in terms of technology. It's a big company, 170,000 employees. And we generate something that I call terabytes of data. Okay, there's a lot of data. And I suspect that many of you have heard the mantra that has come out recently on big data. How many of you have heard this term? Right? All right, so audience participation question number one. What does big data mean?
A cloud.
A cloud. Okay, so the clouds are outside right now, and there are lots of raindrops falling. That's big data clouds. Yes, ma'am?
Our industry defines it as that which does not fit in an Excel spreadsheet.
There is more truth to that than you might think, actually. Anything else? Any other suggestions?
Well, to me, big data is just accumulating as much information on the topic as possible and storing it. So just the computing power now allows you to just get unlimited data. So big data is just dealing with that.
Yeah, it turns out that there are projects in the world. In fact, University of Calgary is involved with the Square Kilometre Array. Any of you familiar with this project? This is an effort that is housed in Australia and South Africa to collect literally a square kilometer set of radio telescopes that is gathering so much data that it has to be pre-processed to actually be stored on disk. That's the rate that the data is achieving. And it's pretty much homogeneous data, right? There's a ton of data coming forward on this square kilometer array. There are other ways of thinking about big data, and I'll tell you the way I think about it. It's actually not cloud. Cloud is more of a processing capability in my way of thinking. But the term of not fitting in an Excel spreadsheet or just taking a bunch of stuff, to me, big data means any amount of data. It could be 1,000 rows in an Excel spreadsheet that I, as a human being, can't process very simply. So in other words, I have to go through extraordinary measures to try to understand that data and gain some insight from it. That's going to be the general theme of what I'm going to be talking about. And I'd suggest that all of you here have been hit with big data in one form or another, be it geometric or non-geometric, because you look at it and it just doesn't make sense. So the other comment that I want to make that's of interest about our company actually was evoked by the person who was talking about is a modular home built inside or outside? Does it make a difference? So Boeing, so I'm in Seattle, Washington. That's my home base. And Boeing has this interesting building in Seattle that's called the Everett Factory. Okay, in the Everett Factory, there are all the wide-body airplanes built. 767, 747, 777, and 787. It is by volume the largest building in the world by a factor of 2. There are storm systems that occasionally appear there. And so my second audience participation question for have any of you seen this building? Yes, there are a couple of people, right? So you can't answer the question. Because you should know the answer if you went on a tour. How much does Boeing spend annually heating and cooling that building? There are roughly 7,000 people who work there on a shift-by-shift basis. Any wild guesses? Any non-wild guesses? So who said 0? Mohammed did. Allison did. The answer is actually 0. Okay, Mohammed, why?
I assume the weather first and maybe technology, and I have no idea.
But that's one of the better. That's really one of the really very accurate answers I've ever gotten when I've asked this question. It actually turns out that it was designed to use no heat or to have no heating and cooling. And Seattle does get hot, And so what happens is that during the summer, the prevailing winds are north to south, and the building was situated so that it's north to south. There are hangar doors at each end of the building, and you just raise them and lower them appropriately to get wind through the building. Cools it off. In the winter, 7,000 people do generate heat, as do electrical lights and the like. And so that natural heating and cooling allows us to heat and cool that property in a way that is extraordinarily efficient, at least from Boeing's bottom line perspective. So I'm going to go through a few things here. I'm going to try to do so pretty quickly in the interest of time and keeping everybody awake at 3:30 and 4 o'clock in the afternoon. So we're going to talk a little bit about how Boeing got involved in changing the landscape of computer graphics. This is a fascinating form of history. I won't have a chance to go through all of it. We're going to talk about some 3D use cases, and then maybe a little bit about where we're seeing as a large industrial company that has similar motivations to where computer graphics and mobile technology is going to evolve in the future. What's fascinating about doing talks like this is I get to see parallels between my aerospace industry and what's happening in the building industry. I think the first talk I gave to sets of people involved in architecture was for a bunch of people who are dealing with geometric modeling. They are doing new ways of trying to generate buildings like the bird's nest at the Beijing Olympics, or the new airport in Beijing, to use geometric techniques to actually help design the buildings automatically. That's at the front end of the business, and Boeing does a lot of that kind of stuff. At kind of the midpoint of is that you wind up doing all sorts of analyses and trying to get the configuration going. So I've talked to people about how Boeing does that analysis. And now I'm talking to people who are involved in the actual fabrication and sales. It's a really interesting parallel to see that my aerospace industry goes in high parallel to what's happening in standard building and construction. There are lots of other parallels that I won't have time to go through. Okay, so let's talk a little bit about what's going on with data growth. Anybody here heard of Moore's Law? A guy named Gordon Moore in the early 70s had a correct prediction that the computing transistor would double in speed every 18 and double in speed every 24 months, and cut it in price by half. So the computing power that I'm carrying on my cell phone probably has more power than the entire fleet of NASA space, the space shuttle, the space station, etc. The interesting part is that a human brain doubles once every few million years in terms of capacity. And in fact, this graph is actually representative of my brain right now, except it's kind of going down, right? From a very long time ago. What's interesting is that the growth of the data growth is actually faster than the slope of computing technology. So we're generating more data, and we're getting to zettabytes, which is 10 to the 21st bytes of data. So that's starting to get to really big data at that point. And the interesting point is that we as human beings still want to understand it. So one of my favorite lines ever was that we create something called write-only memory. That you store it and you never look at it again. Have any of you ever done that? I know I do that a lot, because all of a sudden I just have so much stuff that I put it someplace and I never look at it again. Email hits me this way, because I get so much email that I can't read all of it by any stretch of the imagination. I can imagine that happens at least to half the audience here. But it turns out that visualization is really fascinating, because over 80% of all the communication power that we have in our brains is dedicated to processing visual techniques. So that's why I'm a visualization zealot. I think it's a way of communicating lots of information very quickly to a large number of people. And then you have to understand, what can you do with visualization alone? And so we've actually done some work at Boeing trying to understand a taxonomy, a set of tasks that people can do just using visual analysis. So I can do everything from finding a really simple, a really specific object in a highly complex scene, to look at how surfaces work, because aerospace really cares about how surfaces are done. I can visually scan the scene, and I can find all the people who are starting to fall asleep already in this room. I can also focus, like you learn in public speaking, on people that are listening carefully and that you can communicate with on a one-on-one basis. I can look at two different versions of the same product and understand differences. There are lots of things that you can do just looking at visual task analysis. I'm going to talk about a number of things in terms of what Boeing has done with computer graphics, and then spend most of the rest of the talk talking about a field called visual analytics, and then another called massive model visualization. So hopefully you'll be able to bear with me through this. So this was kind of an interesting piece that I came to learn about 4 or 5 years ago. And most of you have heard about computer graphics for a while. You've watched all the Star Trek movies. You've watched all sorts of special effects that are being done currently. And it turns out that Boeing, a guy named Vern Hudson, coined the term computer graphics in the year 1960. It's obviously still in force today. A fellow named Bill Fetter popularized it. What I'd like you to notice in terms of the visuals that are supporting this slide is the really cool hairdo the lady has, number one. And also to understand that the input mechanism, and we're going to get back to this towards the end of the talk, take a look at the input mechanism. How many of you have actually seen or encountered a punch card? Anybody? Okay, well that's actually a pretty large percentage, about half. For those of you who haven't, it was the curse of the 60s. Okay, you really didn't live in the 60s unless you actually saw a punch card, because you couldn't erase anything on it. You had to start from scratch. But notice also that Boeing was doing 3D to 2D plotting in 1960, trying to understand the three-dimensionality of objects. We also started playing around with how people interacted with certain spaces. So Fetter, again, did this thing called Bowman that actually allowed people to investigate reach studies on the bridge of a ship. So you could try to understand how well a person could reach out and simulate it before you actually built it. Okay, pretty cool stuff. Any of you Star Trek fans, the movies? So there's at least one Trekkie in every crowd. This is good. and the best part is they admit it. So a guy named Warren Carpenter developed a technique called fractals that were used for the Genesis effect scene in Star Wars, in the Star Trek movies. For those of you who recall the first 2 movies, there's a planet that kind of forms out of nothing and a fire goes over it. And Lauren actually did that while he started that fractal development while he was working at the Boeing company, which is pretty interesting. I mentioned augmented reality, and then again, a really cool hairstyle from the early 90s. Another Boeing person named Tom Cadell actually wound up inventing the term augmented reality. The idea is really fairly straightforward, and it's something that has large potential impact. It hasn't quite been realized yet on both the aerospace manufacturing industry and on the building industry, because what it winds up doing is allowing you to project instruction and the like of a virtual type on top of a real scene. So you can put in instructions and try to tell people what to do virtually, and that is augmenting the reality of what you're actually looking at. Tom had an interesting headset here. They were trying to figure out wire bundle routing, how to work with wire bundles on airplanes. That's a whole different story. There's a scheme called massive model visualization that allows you to look at an entire airplane in real time at interactive rates. And I'll talk actually about some of that, why that's important towards the end of the talk in terms of massive model visualization. And we've got this field called visual analytics that I'll also talk about. So we have a long tradition in computer graphics and computing technology, and in fact, we pushed the state of the art in computing technology as much as any industrial company in the world. What we wind up doing in aerospace is that we have to push the state of the art in order to build really complex state of the art products. And it takes a long time for that state of the art technology to become widespread. So let's talk about some uses of computer graphics. We'll talk about visual analytics and 3D geometry visualization. One of the things, as all of you who are in this room are cursed with in terms of computing, is to understand why something is when something is interactive and when it's not. So these are some measures that we have developed over the years through empirical research at Boeing that basically says getting something started fast is good. People don't like to wait for a long time to figure out if their session is going to be worthwhile or anything. And then there's something that you have in terms of dealing with 3D. So how many people are dealing with 3D computer graphics in one form or another as part of their jobs? Okay, that's about maybe 20%, I'd say. Are any people investigating use of 3D? Okay, so there are people that are starting to get what 3D is all about. Some of the stories that I'll tell you towards the massive model visualization is where that 3D visualization turns out to be really advantageous. And the idea is that you have to be able to work at interactive rates with large amounts of visual data in order for that data to become effective, for that to be really interactive. And that's where this thing called the human flicker fusion threshold comes in, which was developed as people showed film, right? You had to understand when the brain actually thought it was moving. Because if you look at a film, you know, it's just a series of stills. If you don't do it fast enough, it looks choppy. If you do it at the right speed or faster, it looks really good. So 16 frames per second is the absolute bare minimum. When you're holding something like a mouse or doing interaction, you can get by with 10 frames per second. What is fascinating about the world of 3D is just about everybody who's coming into the workforce. So I'd argue that the people who Boeing is hiring as manufacturing technicians or mechanics, that people who are in the trades in the building industry are coming predisposed to working with 3D. So how come? Why are people predisposed to work with 3D?
Gaming.
Gaming, electronic gaming. How many students here play games? Oh, come on, you're all kidding. Oh, how many non-students play games? But seriously, the people that Boeing is hiring all have a grasp for wandering around a virtual environment in 3 dimensions. And so don't fight it. You might as well adapt a little bit because it's a lot easier. And then we have to always work with graphical selection so you can find out more information about it. I've done a lot of work in Canada over the last 6 or 7 years in this field of visual analytics. Boeing has been incentivized for a number of things in terms of industrial participation and the like. And I've been lucky enough to form some great collaborations with the University of British Columbia, Simon Fraser University in the West, with Dalhousie in the East, OCAD University in Toronto. So there's been a lot of really cool stuff that we've done that tries to worry about how you can take large amounts of non-geometric data and make it work even through the limitations of Excel. Because in reality, the primary tool that people have a tendency to use in order to figure out what's going on with this non-geometric data is the Excel program. So the distinction is that, do you get what the distinction that I'm trying to make between non-geometric and geometric data? It's relatively straightforward. Right? And you'll see examples of geometric data a little bit later. But the idea is that we're trying to build some science around this whole process of understanding where visual analysis can be extremely important. That includes the cognitive processes, it turns out that one of the really key difficulties that we have when we acquire all of this data is actually finding the mechanisms to allow you to get the data back out again in order to use it and understand it more effectively. We've got tons of tools. We've got techniques and methods to use those tools. And last but not least, actually Dale and the sales staff is, how do you put together a compelling story that lets the data that you've acquired convince Allison that, in spite of the risk that the CMHI back office has, that you should grant this person a loan. And that notion of coming up with complex communications is a really hard thing to do. I don't know how many of you have that as part of your jobs. I certainly do. But in reality, as your students and the like, you're going to have to convince people that what you have done is correct. And that's actually another type of analytics. But if you take, there are a few key takeaways that I'd like to have in this talk, aside from thinking about the parallels between what you're doing in the business world and in the building world and what I'm doing in the aerospace world. One of them is that interactivity is really important. In other words, especially as you're dealing with these crazy computer systems, pay attention to just how interactive it is, and don't accept bad, subpar interactive techniques. The other is that we are in a world that says that you can do lots of non-geometric analysis, but it turns out that we do tons of analysis with tools other than Excel, because we have a number of different situations that we have to deal with. So if you're trying to gain insight into this non-geometric data, think about things that you have a tendency to want to do. Right? You want to gain some notion of situation control. This is something that you do conventionally in a military operation. You want to understand where your troops are deployed. You want to understand how to move them around. It's very often what happens in a command and control. We also wind up doing a lot of tracking and visibility. So that's near time, near real time. Situation awareness tends to be real time. But you're trying to determine status. Where are those parts that were supposed to be delivered to my plant or to my building site? Where are they? I'd like to find out where they are so I can plan my workforce accordingly. How can I deal with supply chain issues? How can I understand statuses of where my build process is? We do this at Boeing all the time. We've got dashboards that you can't imagine scattered throughout the factories and the like to understand how we can keep track and optimize the performance of our workforce. We wind up doing things that try to figure out, why did something bad happen? So there was a huge investigation into the 787 battery fire. People were scurrying around trying to find out, why did that fail? We do it a lot in airplane safety, and I'll give you a really interesting example of where it happens in airplane safety. We do scientific methods. We postulate things. We say, if something is true, then something else. This is a scientific method. And then we try to prove or disprove the hypothesis. As an old science guy, I really like the scientific method because you can come up with some deterministic conclusions and reasons why you should proceed a certain way. Boeing does an awful lot of stuff, and the intelligence community does an awful lot of stuff with determining anomalies and correlations, especially when there are anomalies. And so the intelligence community really cares about how, when something happens out of the ordinary, you generate a blip and all of a sudden your intuition says that you want to investigate more. That's a big deal, and visual techniques are very important there. Very often you want to try to predict something. Again, going back to the supply chain example, you want to understand how you can get quantities of something to your site fast enough so that you don't overbuy or underbuy. You want to get the right amount. Boeing does this in spares a lot, so we don't want to have too much inventory on stock because it costs too much. As a company, I think Boeing probably does this more than any other company that I know of. It's certainly because of aerospace products, is that it's really expensive to build complex things like wind tunnels, certain testing rigs for aerospace products. So we wind up doing trade studies, what-if studies. If I change this value, what's going to happen to the system that I am working on? Computational fluid dynamics, structural analysis. All of these technologies have permeated the automotive business. My contention is that a lot of it is going to be starting to come into even more complex studies in the building industry, because all of a sudden you can pre-qualify your product a lot more quickly than you can in other ways. There's a really cool display out in the Space Museum that is the wind tunnel that was designed by whom, Mark? Turnbull. That talks about the way he recorded all this stuff. Boeing doesn't use wind tunnels very much anymore. We wind up doing all that analysis using computation fluid dynamics, because it tells you the performance characteristics, and we can optimize the designs to provide much more fuel-efficient products. And I talked a little bit about the summarizing and communicating results. Lots of tools and techniques. I'm not going to go through all of these by any means. Visual analytics is an emerging class of analysis tool. Here's the key point. In addition to understanding the types of insight, not every tool is created to solve all problems. This is in spite of Microsoft marketing of Excel. Right? So you all know, as people who are involved in manufacture, that you can not always use the same size hammer or the same size saw to do certain jobs. And this is true in the computing world as well. So this is an attempt to map types of analysis to certain tools that we have floating around Boeing. And quite honestly, the list of tools extends far beyond the right-hand side, my right-hand side of this slide. So be careful and understand how to map the right tool to the right type of analysis. This notion of visual analytics came about because primarily of the results of 9/11/2001 in the US. There was something that happened that was anomalous. If we had been able to detect it better, we may not have had that anomaly. And there were things that happened in the causal chain analysis that led to that. So here's a cogent example. This is what happens. So you all know about birds, right? You have birds in Canada most of the time. Right? I think they're still around. In spite of the rain, they show up every now and then. If you are a flyer, and I fly around a fair amount, there's one bird strike every 2,000 flights or so. So you think about that in terms of jet airplanes. There are about 20 strikes per day. And interestingly enough, those are just the reported strikes. There are probably another factor of 4 to 5 more strikes that occur on a daily basis that go unreported. There's all sorts of things that contribute to that, and we actually have flocks that fly after things. This is the kind of damage that can be done. This is just a few ducks that ran into a 767-300 as the aircraft was leaving Paris. Come on, there we go. So here's some of the stuff. So we actually worked with a bird strike expert, a fellow named Roger Nicholson at Boeing, and a student and an intern from Simon Fraser named Andrew Wade. And these two wound up going through a bunch of data that was inaccessible by Excel with a different set of tools. This image is from a tool called Tableau. And among other things, they geolocated where bird strikes happen in terms of time and location in the United States. And I'm sorry we didn't put Canada on this chart, but this is a US-centric study. And the message that was clear is, when you look at this data, this is not normalized for time of year, although we could do this by time of year. If you look at this data, what strikes you as being of interest? Anybody? One guess. Huh?
During the day, there's a lot.
Yeah, a lot during the day. Anything of surprise? What surprise? I know I was surprised when I saw this data.
A lot at night.
At night. yeah, this is really kind of interesting. Because pilots, aside from sleeping at night, hopefully while they're flying they're not sleeping, but nevertheless, what happens is that pilots need to be aware of bird strikes at night. Why? Migration, exactly. So birds fly up and down, and notice the corridors that are highly saturated, especially at night. So you find this out, and all of a sudden, you find out that you can improve pilot training to be more sensitive to bird strikes, to understand where they happen and when they happen. You can understand more and more about where you should place certain exposed items on a fuselage by looking at this bird strike data. And these guys did this work in 2-day sessions over a period of about 3 months, and they just blew everybody away in terms of who was doing the analysis. Okay, just by looking at data and gaining insight. This is all non-geometric stuff. The other non-geometric example comes up that affects this audience quite a bit, is how can you improve the tasks that people do on a routine basis and prevent issues and injuries. So what happened is that a lady named Melissa Finlay worked with another set of students from University of British Columbia and discovered some really interesting things about certain processes that happen. First of all, she figured out that she had to convince her management that this was indeed a problem, and actually was able to show the cost data of repetitive stress injuries by looking at extant safety reports and cost and lost worker hours. And it turned out that she found certain areas, certain tasks on the factory floor that caused more and more repetitive stress injuries. As an ergonomist, she was able to change a number of different worker positions, and you just keep going and grinding away at it, and all of a sudden your factory productivity and your manufacturing processes improve. Your worker health improves, your worker safety improves, and all of a sudden you've got a win for everybody. Pretty cool, just by looking at data. And the reason that Melissa got involved in this is because she couldn't do anything in Excel anymore. Just blew her away. So let's talk about geometry data and its visualization techniques. So most of you are familiar, we kind of brush non-geometric data under the covers, right? That's just HR stuff, it's just finance stuff, right? It's just the numbers that you collect from your sales figures. Dale probably doesn't throw the sales figures out very often. But you track these things and you understand them over time. It's all non-geometric. Boeing started out in the geometric world by saying, we want to design our products in 3 dimensions. Okay, we started doing that in the late 80s, early 90s. And the 777 airplane, the Boeing 777, was the first complete digitally designed airplane done fully in 3D using solid modeling. What was interesting about the transition in terms of the FAA, I resonated a lot with Adair's comments about standards and what influences the building industry, because it turns out that the aerospace industry, the FAA, the JAA, all of the U.S. government in terms of military products, has a set of just as conflicting, inaccessible standards as the building industry does. One of my favorite quotes was, their standards are great, there are so many to choose from. Because they don't always agree with one another. And they compete with one another. Right? It's just part of life. And one of the things that the 777 had this really interesting feature. We designed it all with solid models, did all the finite element analysis, structural analysis, the weights, all that kind of stuff using solid models. But when it came to the factory floor, what we had to deliver to the factory floor was engineering drawings. Standard 2D drawings, because that was considered authority by the regulatory agencies. And it took Boeing quite a while to get to this point where we actually define geometric dimensions and tolerances and the like in model-based definitions and the 787 actually delivers to the factory floor and to customers 3D models that have annotations and the like, so that people can actually build to tolerance and build to the specs that the engineering staff has designed. And we have a big problem with product structure. So if you look at where visualization data falls in a continuum, you've got those three components. Okay, product structure, you have to figure out how it all hooks together, because nothing is more embarrassing than trying to assemble 2 million parts into a commercial airplane and having stuff left over. You know, it's just not good practice, and so we have to figure out where it all goes, how it interferes, etc. We have to understand the tolerances as well as the geometry. So there's this notion that you'll be hearing as you work and get into the world of three-dimensional geometry and the like, that there's high end and low end. Okay, there are use cases that are clearly low end, where you don't need a whole lot of data, that range at maybe 1,000 parts. How many parts are in a mobile home or in a modular home? I don't know. I'm asking. Somebody has to know here, or maybe not. Yes.
We did a study of a small 5,000 was our number.
Okay.
Yeah.
So 5,000 parts, maybe pushing up to 8,000 to 10,000 on the high end. So you're sitting at kind of the kind of this spot here on a log scale in here. So you're not dealing with a huge amount of 3D data, but still things tend to grow. To give you an example, Boeing built the 777 with roughly 350 million polygons. This is an interesting measure. There are 350 million polygons roughly in a 777. There are about 650 million to upwards of 1 billion in a 787. As designers get more comfortable with the 3D paradigm, as designers are and engineers, they just add more and more stuff and more fidelity to their models because they can do better analyses of them. So this is an issue of low-end visualization because we have to deliver this 3D geometric data to folks. And here are some examples of what Boeing is doing. So this is 787 is actually delivering engineering drawings to the shop floor, to the quality, to everybody who's inspecting the airplane, looking at how to deal with geometric dimensions and tolerances. We're delivering 3D work instructions to the factory floor. We're not doing it via augmented reality as yet, but there are instructions that basically tell you the assembly sequence because, as is the case in the building industry, the FAA actually certifies process, the build process, not necessarily the final product. Unlike the build industry, Boeing, because people are spending like couple $100 million on an airplane, the airline companies actually send representatives to do inspection tours of their jet before we turn the keys over. And we actually do turn keys over. And when the key gets turned over, the money transfers from them to us, which we're happy about. But nevertheless, we're trying to get people to understand how to build things in 3D because you can show the way people should build stuff more effectively that way. This is where performance and scale are critical. High-end visualization is what I was talking about with this massive model visualization piece. I'm going to show you a little bit about how that works. But think about potential applications of, let's say you wanted to look at the entire digital design in full reality of what's going on with your product as we want to do at Boeing. There's a lot of use cases that you've got that range from being able to design in context all the way that you can do from working with human models. What I found particularly fascinating in terms of looking at things like the structure of the 787, the interior detail, something like the 787 in flight. People are designing and building the product in a reasonable manner using these 787 drawings because you have to understand, and this is true, I think I'd argue in large part in the building industry as well, that you have to understand that there are certain things that just shouldn't touch one another. Okay, I will argue that commercial airplanes and aerospace vehicles have a lot tighter space restrictions than the building industry. But still, if you get things in the right place, you prevent things like nails or other things going through objects that they shouldn't actually go through. I actually have personal experience with that, but that's a different story. Nevertheless, that's product design review, data design review. What has happened, and this is another message that you all should think about, especially in the build end of the manufacturing of the home site, is that we are finding extraordinary value in looking at these complex models for a number of different scenarios that are represented on this chart. It ranges from what should be in the airplane as it rolls down the assembly line at any point in time. Because it's important for the people who are building the plane to understand that, hey, you know what? I should have these parts on the plane at this point. I don't have to worry about the rest of the stuff that will be assigned, that will be done later. And seeing that visually turns out to be extremely valuable as people are building the plane itself. It turns out that other things that you can wind up doing include figuring out exactly what section of the airplane you are, and you can do this interactively and quickly. Another thing that turns out to be fascinating is that you can say, I have a customer, let's say it's Air India, and the next plane that I'm building down the line is from, I don't know, Air Canada. We'll let Air Canada be our guinea pig. There are differences in the way those products are built that are not easy to understand without using visual techniques. So we're using visual techniques to actually highlight the differences between those two products. And I'd argue that this happens in any manufacturing, any manufacturing situation, that you need to understand where things are different as well as where things are the same. In fact, the other thing that's turned out to happen, I imagine this has to happen in the building industry as well, is that Boeing occasionally gets situations where somebody screws up. You know, you get it's called in the aerospace world, it's called a non-conformance. Okay, in the software world, it's called a bug report. What do you call it in the manufacturing world? In the building world? A screw up? And this happens frequently, but so what happens is that the technician, has to enter not only the part that's messed up, or the person who's inspecting for an airline, they want to indicate the part that's screwed up, but they also have to tell you where that occurred. Okay, and the way Boeing does it is by having an XYZ coordinate. That's a pretty accurate way of doing so. Until you figure out that the people who are entering the XYZ coordinates do so in a way that varies significantly, and it's very often incorrect. And so what happens is that the XYZ coordinate gets entered, some report gets put in that's in unintelligible English, and the item goes to the quality inspectors who say, you know what, that XYZ coordinate isn't quite right. Would you please re-enter it? And the tech goes, well, I entered it. Go send it back to the quality guy. So it goes back, it's kind of this ping pong match between, I know where it is, I told you where it was, I don't believe it. Please enter the data correctly. So we've stopped that. We're using these digital models by letting the system say, this is the XYZ coordinate when you click on a part, and all of a sudden you get an accurate XYZ. No mystery. Just by using technology in a different and innovative way that shortens essentially the bug reporting cycle. We do reach studies. We do ergonomics analysis of how people interact with the airplane and how they do things for producibility. So we actually understand how to build things more efficiently using computer-based techniques. We actually tell airplane mechanics how to repair airplanes that have been grounded for some reason or another by providing them a complete 3D model as well as all of the engineering, as well as all the reference engineering data, and we call it the airplane in a box for airplane on ground. So I'm going to do a quick demo. So here's where the risk comes in. Because I know all of you wanted to see the insides of a 787. And I'll fly in here. And you can see what the newest Boeing airplane looks like. And so this is a live demo. You see underneath the seats, so if you wanted to, and so these are views that people rarely get. I haven't ridden in true economy in terms of underneath an airplane for a long time, in terms of the baggage compartment. So this is the baggage compartment on the 787, and what I'll wind up doing is flying into this area here. So this is one of the electrical, this is one of the electrical engineering bays, the electrical bays on the 787. To give you an idea of the complexity, there are about 60 miles of wire on one of these airplanes. On an A380, there are about 180 miles of wire. It gives you an idea of the complexity of the items that we design and why visual techniques are clearly important in terms of disambiguating where things are supposed to go and how they're supposed to be put together. There's not a lot of question that the engineering design can be really well kept. Now, I'm not going to bore you with all the underlying technology that goes into making this work. So I'm running this demo, which is about 10 times the memory capacity of my 5-year-old laptop, without any additional hardware, with just a standard hardware accelerator. The graphics machines that your kids have on at home are far more powerful than this machine. Okay, but it's really cool stuff, and we've had a good time doing all this. So that's the nickel demo. I'm going to give you just a couple of things, and then I'll yield the floor to Dale in the interest of time and sanity, mostly yours. But the point is that you have to understand that computer graphics, like all technologies, goes in cycles and waves. Early on, the world of computer-aided design and manufacturing that I got involved with and kind of bitten by in the early 70s and the like, kind of lasted until 1990. What's happened today is that arts and entertainment have taken over this world of computer graphics, and just about every movie that you see, there's, I'd say, probably at least 50% is overwhelmed with computer graphics techniques. The video gaming technique. I don't know what the third wave is. My reality is that the third wave is going to be something that, in reality, is going to clearly understand how to deal with things that are at the ultra high end, very large displays. More importantly for our workforce, we have to understand how things are going to happen at the low end. I'd argue that this is identical to what is going to happen in the building industry. Because one of the things that Boeing is motivated to do is have the people who are developing who are building our products, not go around and search through manuals and try to figure out where is the documentation that lets me do this. I'd argue that this happens as well in any manufacturing process that has a lot of human beings involved. And the building industry is certainly a great example of that. Mobile devices have a lot of improvements. What we really want to do is understand that there's a lot of magic that happens in making all this stuff work, just in making the things work that I showed you. The reality is that there are lots of technical challenges, but the way people effectively interact with their environments, especially in this mobile world, is something that varies a lot from what we've done in the past. And it's going to cause a whole lot of revolution in the computing industry. It's certainly going to cause a revolution in what we do at Boeing. I'd argue it will do the same in the building industries. So that's it. On time, 4:28. Look at that.
Do we have a couple of questions for Dr. Kasik?
First class.
Sure. Let me get up there. Yeah, I'll fly while other questions happen here. Actually, what's really cool to look at is the cockpit too.
Dave, this is probably off track, but I flew out here in a 737-700, and I know they had a few problems with hard over rudder problems a few years ago.
Oh, yeah.
And I was thinking all the time, I'm sure if that doesn't happen, I'm sure it would. But I'm thinking with what you're doing on the 787 and those the fiber graphics.
Composites, yeah, all the composites, right?
Does this system have the capability to almost do that wear analysis? I don't know what they did to solve that hard over rudder problem, but obviously with the technology here, does this have the capability to do that sort of analysis, like long-term maintenance and things?
So this system per se doesn't. But remember that I talked about one of the big uses of what-if studies as a form of analysis in the Boeing company. There is an awful lot more more attention that's being paid to in terms of where the what's going on with how to build more reliable things that last for years and years. And you've got to understand that that Boeing builds products that last for about 50 years, roughly. So I haven't gotten to first class, but I'm trying. This is why they pay me as a computer guy, not as a flyer. Go ahead. Here's one of the galleries. Go ahead. More questions?
Yeah, what happens with this technology outside Western needs? It's all great that you have the capability and you have the equipment to do the search and analysis, but what, does that mean that airplanes are going to have to come and be serviced in different countries so that they can get the maintenance that are required? Because not everybody will be able to catch up with this technology.
That's actually a really interesting question, because the third world countries. So first of all, the universal language of aviation turns out to be English. So you're kind of stuck with English. Secondly, there's some clear advantages to dealing with. By the way, I did fly through first class, and I'm trying to get to I don't get to ride in first class frequently, so. Nevertheless, what happens is that the visual techniques translate in a far more language-independent manner than most other techniques, right? Than written. But this is what the cockpit looks like. Anyway, so what's even more fun is to go underneath, see all the stuff that's underneath the cockpit. You can spend hours doing this. I've often thought that we should just actually take this and make it one of the really cool video games of all time. Because you get all this spaghetti that happens underneath. They're really complex systems. Anyway, so seriously, the visual metaphor, the visual paradigm helps an awful lot with that language problem. Okay, so it is something that we do in fact consider. It's an appropriate question. Thank you. All right. I'll turn the microphone over to Gail. Thank you very much. And thanks also to Kathleen and to Dick for being a fine hostess. Thank you.
I thank Dr. Kasik. Your neighbor, Mr. Gates, must be really happy about Excel when you started explaining it this way.
He got on my, so Steve Ballmer did.